Hello, welcome back. In this video, we are going to discuss about simple Rankine cycle, which comes under the vapor power cycle of module number 3 in applied thermodynamics syllabus. And particularly, we are going to discuss about the very TS diagram of simple Rankine cycle and its description, as well as we are going to analyze its performance by means of deriving its efficiency. This is how a simple Rankine cycle look alike, and this is the schematic diagram which represents simple Rankine cycle. Rankine cycle is a theoretical cycle on which the steam turbine or engine or steam engine or works. It's a steam turbine engine also, we can call this as a steam turbine engine as well, gas turbine cycle as well. We can call this as a gas turbine cycle as well. The four processes in this are 4 to 1 is a boiling process which happens in the boiler, where Q1 is the amount of heat added into the system, and the second process is the turbine where expansion takes place. Now is isentropically it takes place, or reversible adiabatic expansion takes place, where Wt is the amount of work is done by the turbine. At the end of the turbine, the gas is entered into the condenser where it get condensed and become a condensed liquid at the state 3, and this condensation process is constant pressure heat rejection process. Then it's pumped back to the boiler in the process 3 to 4, where we are giving some work input. Because of that, this condensate we can move easily flow into the boiler. And the four processes of a simple Rankine cycle are: first process 1 to 2 is a reversible adiabatic expansion in the turbine or steam engine. The second process is nothing but constant pressure heat transfer or constant pressure heat transfer in the condenser. It is transferred from the system, from the liquid to the surrounding. And the third process is reversible adiabatic pumping process in the feed pump, and the final process is known as constant pressure heat transfer process in the boiler, where heat is added to the system. This is how a typical pH diagram looks like for a simple Rankine cycle. In the same diagram, we have represented the quality of the steam at the end of the boiler. It varies with respect to the quality of the steam. It might be a dry steam or wet steam, or even it might be a superheated steam. Based on the quality of the steam at the end of the boiler, the pH diagram and TS diagram varies accordingly. These two represents a TS diagram variation for various quality of the steam at the end of the boiler, as well as HS diagram of the simple Rankine cycle. Now let us go and analyze what is happening inside the simple Rankine cycle. For this, we need to consider 1 kg of fluid, and we need to apply the steady flow energy equation to the boiler, turbine, condenser, as well as the pump, all four components of the cycle. First, we will analyze what is happening with respect to steady flow energy equation. First, we consider the boiler. When we consider boiler as the control volume, we get HF4 plus Q1 is equal to H1. Whereas from this, we can easily calculate amount of heat added as Q1 is equal to H1 minus HF4. HF4 is the quality of the steam, or wet steam or fluid steam, steam and the water condition at the starting of the boiling process. Next, if we apply or if we consider the control volume as a turbine, we get H1 is equal to Wt plus H2, where Wt is a turbine work. From this, we can easily calculate the Wt, the turbine work, as H1 minus H2. Third, if we consider the control volume for the condenser, we get H2 is equal to Q2 plus HF3. From this, we can easily calculate the amount of heat transfer from the system to the surrounding, Q2 as H2 minus HF3. Then final focus or final control volume focus will be on the feed pump. For feed pump, that steady flow energy equation looks like this, that is HF3 plus Wp is equal to HF4, where from this we can easily calculate the Wp, the work of pump or pump work, as HF4 minus HF3. And now we know that the efficiency of the any cycle, the Rankine cycle efficiency also defined by the output to the input relation that indicates the net work done to the heat supplied. Net work done we can further simplify in terms of the difference between the turbine work to the pump work, and replace all the values which we had derived in the previous slides into this. We get final Rankine cycle efficiency as H1 minus H2 minus of HF4 minus HF3 divided by H1 minus HF4. And we know that for a reversible adiabatic compression, we can also relate the TDS, the amount of heat transferred to the system, in terms of TDS as TH minus V into dP. Since ds entropy remains constant in this process, so ds become 0. So dH minus VdP is equal to TDS. From this we can calculate the dH as V into dP. So HF4 minus HF3, that is the difference between the enthalpy, is equal to V3 at this state 3, and the difference between the initial and final pressure P1 minus P2. If you substitute all these things in the previously derived Rankine cycle efficiency, we get final output as efficiency neta as equal to H1 minus H2 divided by H1 minus HF4. And to make it simple, and I know I just enclosed the animation video how a simple Rankine cycle works in the following 2-3 minutes. It will make you to understand more clearly with respect to how a simple Rankine cycle works. Just watch this video, it will give more clarity with respect to the simple Rankine cycle working process.
To make a Rankine cycle, we need 4 processes. Process 1 to 2 for the boiler, process 2 to 3 for the turbine, process 3 to 4 for the condenser, and finally process 4 to 1 for the pump. And that is what we are going to discuss for the next part. Okay, so let's get this started. For process 1 to 2 boiler, these are the things that we need to remember. Since boiler is a heat exchanger equipment, a heat is added into the boiler through a fuel, which may be coal, oil, or natural gas. Here, water is converted into steam or superheated steam. This is an isobaric process or a constant pressure process. The temperature and entropy for this process increases. And we can solve the heat addition by using the formula heat added equals fluid energy out minus fluid energy in, or enthalpy out minus enthalpy in for the boiler. Note that this equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting pressure drop. So those are the important things that we should remember with understanding the boiler process. Now, steam can be used in the next process, which is the process 2 to 3 turbine. Turbine is a work generator equipment. It contains series of stages or a set of stationary and moving blades to perform its function. By using the steam, work is generated through the expansion of vapor, which may then be converted into electricity through generator. Compared to the previous process, here, since we have an equipment that involves work, isentropic process or constant entropy process is assumed. Yes, it is assumed because in real world, there is no such thing as ideal. On this process, the temperature and pressure decreases. And the formula for the work is fluid energy in minus fluid energy out, or the enthalpy 2 minus enthalpy 3. Note that equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting heat transfer with the surroundings. Steam is now already exhausted, and so we need to take it back again to the boiler, but there is no pump that can pump steam, so we need to convert it first into water through condensation. So this is where our next process comes in. Process 3 to 4, condenser. In order to condense the steam, a heat rejection must occur. Most of the power plants utilize the seawater as a cooling medium to cool down and condense the steam. Condenser consists of tubes to accommodate the heat transfer of steam and cooling water, where cooling water is in a separate stream. This is a heat exchange equipment, so we assume that this is an isobaric process or constant pressure process. The entropy decreases, and the quality of the fluid changes until it reaches a saturated liquid state, so from steam to liquid. The equation is heat rejected equals fluid energy in minus fluid energy out, or enthalpy 3 minus enthalpy 4. Note again that this equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting pressure drop. Last process is process 4 to 1, pump. Pump's main purpose is to convey and introduce back the condensed steam into the boiler. Here, work is needed. That means work is negative. Some plants name this pump as boiler feed pump, and it can be either steam driven or electric motor driven. Again, since this is a work involved equipment, we assume that this is an isentropic process or constant entropy process. The temperature slightly increases, and the fluid is in a subcold region in the TS diagram. The formula for the pump is work equals fluid energy out minus fluid energy in, or enthalpy 1 minus enthalpy 4. Fluid energy out or enthalpy out is greater than the enthalpy in, as the pump have imparted energy to the fluid. Note again that equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting heat transfer with the surroundings. And one more important thing, please remember that the pump has the highest pressure in the whole cycle. Okay, so let's have a recap. Starting from the boiler, we convert the liquid water into steam. Introduce it into the turbine to generate work, and then we condense it into the condenser and pump the liquid water back to the boiler through a high pressure pump.
I hope this video might have given a proper clarity for you how a simple Rankine cycle works. With this, we will close this video and we will meet in the next video. Till then, take care, bye bye, and see you.